Let us try to understand here the fundamental theorem of gradient. Before that, let us just understand the basic fundamental theorem of calculus so that we get to understand the three versions of it. Now it says that if we integrate the derivative of a function, suppose f is a function and accordingly df by dx is its derivative. And if we integrate the derivative of this function with respect to x from some lower limit a to upper limit b, the value of this is just equal to the values of the difference between the values of that function at the boundaries. So if we look at it in a graphical manner, suppose this is a function f of x and we start from a to b, and suppose accordingly there is the graph of df by dx as a function of x. If we integrate this from a lower value a to higher value b, the value of this integration is just the value of f at this particular upper limit b minus the value of f at the lower limit a. So this particular statement is called as the fundamental theorem of calculus. Now here we have seen that there are three types of derivatives involved in case of vector calculus, and those derivatives are namely called as gradient, divergence and curl. So since there are three types of derivatives involved, we will have three such theorems, each corresponding to this type of equation. The first of which has to deal with the gradient of a function. So accordingly it is called as the fundamental theorem of gradient. Let us just go through the statement of it. So since it involves derivative of gradient kind, so if we say that t is a function of x, y, z, three variables or three coordinates in fact, then we have seen that dt is defined as a grad t dotted with dl bar. This we have already seen. So for this function t, we define the fundamental theorem of gradient as over a path p starting from a to b. So we have chosen some path which takes us from point A to point B. Grad t dotted with dl bar. This is nothing but dt. So one kind of derivative of t. It has to be equal to t of b minus t of a. So we can see that this is just the replica of the fundamental theorem of calculus, with the only change that this derivative is replaced by the gradient type of derivative. Now we can always verify this theorem, and we can take an example for this. So let us assume that there is a function t equals xy squared. Now in order to verify this, we have to choose a path, as it appears here that we have to choose a path from a to b. So let us choose a path such that point A is the origin 0 0 0 and point B is just 2 1 0. So this is the initial point, this is the final point. So this A to B could be reached in many ways, so many paths are possible. and we note that z coordinate for both these points is 0. So we need not involve z derivative here. So in that case, dl can be written as just dx x cap plus dy y cap, and dz z cap is just absent in this case. Fine. So this is the point A having coordinates 0 0 0 and 1 2 1 2. So we have a point B here having coordinates 2 1. So from A to B, either we can go along x direction and then along y direction, or we can directly move from A to B in a straight line. So there are different paths possible, namely path 1, path 2 and so on. So if we try to find out this, so let us just label this as path I and this as path II, small i's, Roman type of i's. So for path I, we see that y coordinate is 0. So just remember that from A to B we are going in this manner. So for this path I, the whole y coordinate is 0. So dl bar is just dx x cap, and grad t dot dl bar since t is xy squared, grad t is y squared x cap plus 2xy y cap. Yes, this is straightforward. And since y is 0 here, we are left with grad y. Since y is 0, this term does not appear. So we are left with 2xy just a slight change here. So y is 0. So this is just 2xy goes to 0 and y square also goes to 0. So this entire thing goes to 0. So integral of grad t dot dl bar for this region is 0, or this path is 0. Now take the next path. This corresponds to x being equal to 0, since we are always moving along the y direction. So dl bar in this case is dy y cap. And as we can see, grad t now this x term goes 0, but this term remains. So y squared x cap. So grad t dotted with dl bar will be just equal to 2xy dy, which is equal to, just a minute, x is 2 here, sorry, slight correction, x value is 2, it is fixed. So this becomes y squared x cap plus 4y y cap. This dotted with dl bar gives us 4y dy. Now this can be integrated to get integral 4y dy, as y runs from 0 to 1 for this path. So this is just 4 y squared by 2 running from 0 to 1. So this is going to be equal to 2. Now this is 0 and 2, so the total integral from a to b grad t dot dl bar is just 0 plus 2, which is equal to 2. This is the left hand side of this equation. So the right hand side just says that it is t of b minus t of a. And since t is xy squared, t of b would be just equal to 2 and t of a would be just equal to 0. So this t of b minus t of a is again equal to 0. 0 plus 2, which is, sorry, the other way, 2 minus 0, which is equal to 2. So this right hand side is same as left hand side. For this particular case, we have verified the fundamental theorem of gradient. Now there is another corollary to this theorem. Instead of moving like this, we could have also moved from A to B in this direct straight line path, and we could have calculated and we could have showed that the integral in that case as well would have been equal to 2. It is the same thing. So we see that this integral is path independent. Path independent. Further, since this is path independent, we can choose any path and it will have the same integral value. If this is reversed, so if a to b is this much, then b to a of this particular integral will just be equal to minus 2. And if we add these two, that is going to be 0. And this is such an integral where we start from a and reach back to a. Such type of integral is called as closed integral. So grad t dot dl bar of a closed integral is 0. So these are two important properties related to fundamental theorem of gradient.